thank you. It's such a pleasure to be beaming in. It's only virtual, but because I know the lay of the land there, as Emmanuel said so well, I feel like I'm there with you. I'm certainly there with mind and spirit. And my first slide here told a little bit of the story that Emmanuel told. I started in Wisconsin and went to the University of Minnesota, had every intention, I think, when I started there of going someplace else. But what happened was I met this incredible scholar and wonderful human being, Andrew, who I looked to see if he's in the participants today. I didn't pester him ahead of this meeting. I certainly will need to pester him afterwards, but he is part of the reason why I started. He is the reason why I stayed at Minnesota for all 3 degrees. And in fact, I can still hear him, in my mind. I got an email when I was in Soil Mechanics 2, the second Soil Mechanics class, that I had a conflict, or I emailed my professor about this conflict with the lab. And I got this email back, which in my mind is in Andrew Drescher's voice, although of course it was an email. Why don't you come talk to me? And I went in to speak to my professor about getting my lab section situation sorted out, and lo and behold, that turned into something that would just really alter my life, and has been a wonderful relationship both intellectually and personally. And after that, I did indeed spend some time in Australia. I seized the moment to learn how to surf before being attracted back to the Midwest, and I'm very pleased to be back here at Northwestern. It's tough to decide what to talk about, but in view of being at Minnesota, I just had to go back to my roots, and in fact this is a main thread of my research now that I am sticking with, and you'll see that towards the end. I want to just touch on all of the things that I'm not going to get to talk about. I have varied interests, some in more fundamental plasticity, constitutive modeling. This is some work done in Australia with Andrew Abbo, Andre Lyme, and the late Professor Scott Sloan, who tragically died a couple of years ago, suddenly, too young. And we've done work on yield surfaces and constitutive modeling, and more recently some interest in constitutive modeling. My first PhD student, there's always a story to all of these, is his work was actually on ground anchors and screw anchors, which are sort of intellectually interesting because there isn't much known about the anchor installation process. And we managed to build some models, do some centrifuge testing with the folks at University of Western Australia. My colleague Sam Stanier, whose name you're going to see, he's now at Cambridge, Christoph Godin, and Cyrus Tedeschi is the student who did this. I'd love to talk about this work, and I'd love to talk about it because it's an ongoing interest. One of my students, Anna Stajanali, and I went to a field site, or a home actually, where helical anchors are being installed, and there's a lot of interesting things you can do there, both, as I say, intellectually and practically. And then another one that I just wanted to mention here, which is, again, is sort of a tangent. You feel like there's so many interesting problems in the world to solve, and at some stage you realize you have to kind of focus on something. But we did some work on rockfall protection barriers, which involves plasticity, and again, it's amenable to simplified analysis and more complex numerical simulation. And that's one of the themes that I'm going to go with today. But what I'm going to go with is soil-machine interaction as the theme of the day. And this is going to be an autobiographical and chronological presentation explaining the full story of how I got into these problems, how we started to build models, and how it continues to be an area of interest. And at Minnesota with Andrew Drescher, we started looking at the problem in the lower right. Actually, this was a Minnesota Department of Transportation project where it's a very practical test that they do. They proof roll, they measure the penetration depth of wheels to see how well they've compacted soils. And Andrew and I embraced this as a pretty interesting plasticity problem, and actually a very elegant one, where the inverse analysis problem, where the idea is to relate the penetration depth to the strength of the material. And we envisioned at that time, even this might look familiar to some, I borrowed this from slides that I had put together even when I was a PhD student at Minnesota, problems in mobility, problems in off-road, where for off-road vehicles, land damage. We envisioned lots of ways that this could be interesting. The theme of the day that I want to go with, and I can start to slow down here, this is part one. I'm going to stick with wheels for the time being, but the theme of my presentation is going to be, which of these is the high fidelity model? We do work on numerical simulation, the underpinnings to make those simulations work, running the simulations themselves. This, in fact, again, is work from University of Minnesota, a three-dimensional finite element simulation of a wheel rolling across a bed of soil. And the question here is, you can do that. It's feasible to do that. You can also build these simplified approximate models and build analytical solutions for these. And one of my frustrations, I gotta say, as I've gotten into this, maybe not a frustration, that's a little too strong, is that people perceive the left picture to be the high fidelity model. And I'm gonna throw my colleagues at Caterpillar, the earth moving company, the heavy equipment manufacturer, under the bus here and say, they call these high fidelity models. And they use the term low fidelity, medium resolution, medium fidelity models for anything but this. If you're using equations, then it must be low fidelity. And I understand the drivers behind that. One is that you really generate beautiful pictures immediately when you do three-dimensional simulations of any kind. I'm going to argue today, for the sake of being provocative, that actually that's the thing on the right that's the high fidelity model. And you'll hopefully be a little more convinced of that if you aren't already. In terms of what we can see when we start to build these models. And I'm going to stick with the wheel for now. I'm going to stick with this rolling wheel problem and do show some work that we did after I left Minnesota, because it was just there for the picking. And I have to say, what drives these models is the fact that I'm an engineer at heart, and engineers contribute this to society, the fact that it just has to get done. Many of us are mathematicians and scientists to various degrees, but what makes an engineer is that at the end of the day, I've just got to get a solution. I've just got to get the job done. So this chap, who shall remain nameless, of course, is just getting the job done. It's hard to get down to, you can't investigate the bottom of a shaft if the shaft is too small, to crouch down into. So this chap here went in head first, thinking of safety, of course. There's a strap around his waist so that he can get pulled out of this at short notice. But this is, an engineer at heart. And this is not, of course, me. But, if it were me, this would be in the proud tradition of some of the things we do at Northwestern. George Osterberg apparently had a reputation for going down into the bottom of caisson shafts, drilled shafts in his suit and tie. And so that would be, of course, a proud tradition of Northwestern if it were me. So here's the brutal engineering approach to solving this problem, which now I won't make so brutal. I think it's elegant, but we're going to make some very strong assumptions here. If I have a wheel that's rolling across a surface, and I'm going to assume steady state conditions, you don't really need to assume steady state at this stage, but it helps to think about this problem this way. There's a wheel rolling across the surface, and I'm interested in predicting, for example, the horizontal force F, depending on how much weight W is on the wheel and how much torque Q I apply to this wheel. And with total generality, I can write here that the wheel is in contact with the soil. The contact length here is H, and the contact angle is psi. Now, the part of the assumption, what drives this assumption here, is that somehow these forces that you're interested that are acting at the axle have to correspond to the forces that are acting over the contact length here. And these I'll denote as V, H, and M, in keeping with what we do for combined loading problems in geomechanics. And actually, the moment that I've written this picture, an approach sort of springs to mind, or should, if you're familiar with VHM envelopes and bearing capacity problems under combined loadings. If I make a set of standard assumptions, plane strain, a 2D problem, that's a rigid wheel, or maybe even a flexible wheel with a nominal radius of some sort. If I assume it's quasi-static, and here I'm going to assume that this is basically clay. There's an undrained shear strength, and it's rough contact, so at the interface, you mobilize the full undrained shear strength of the soil. One strength parameter, the undrained shear strength for say, a saturated clay. Now, I don't know the contact angle H yet, and I don't know the contact length H and the contact angle psi. But I can immediately write down, and if any of my students from statics, I advertised this in my class, have beamed in today, this is something we're doing in statics at the moment. You can relate the forces at the center of the wheel to the forces on the over the contact length through these three equilibrium equations here. Two force horizontal forces sum to zero, vertical forces sum to zero, the moments sum to zero. And the thing that springs to your mind if you've studied VHM, problems, combined loading problems, is I can use perhaps some of the results that are already out there. And what I've grabbed here is a very nice paper by Susie Gorvinick. This solution that I'm going to use actually precedes Susie Gorvinick, goes back to Green, I believe. And that is solving for the load combination that leads to yielding on the interface. These are the equations if you're interested over here, but you don't need to pay attention to these if you don't want to. What really matters over here are the yield envelopes. On the left, or on the vertical axis, I've got horizontal force H, normalized by the undrained shear strength in the area of the footing. On the right, I've got the vertical component of force, or I should say normal, so I'm using the same terminology that's in the literature, but normal force, V in this case, normalized by undrained shear strength and the area. And what you can see here are envelopes for different values of the overturning moment normalized. If I have no overturning moment, if m is equal to 0, then I get this blue envelope. And it makes a lot of sense. As I increase the weight, as I go in this direction and I increase the weight, the amount of shear, the amount of H that I'm going to be able to apply for an undrained material, for clay, for something that's a pressure independent material in terms of its yield response, I'm going to get no change over some range of weight or normal force. And then as soon as I get enough normal force there, I'm going to see a sharp decline in how much H I can apply, how much shearing resistance I'm able to mobilize. And it drops off and eventually reaches a point here which corresponds to the bearing capacity when you don't have any H. This is just pure V, pure vertical or normal loading. And this is recognizable to some as 5.14, Prandtl's number that he derived a long time ago. At this stage, if you're willing to make this assumption that on this interface you have to obey the yield condition, life gets really easy. And actually, I'm going to do a couple of things that make life even easier. I can assume, we thought about this for a while, my colleague Sam Stanier and I, but we can assume reasonably that the overturning moment at the interface is 0. So that's something that would be a subject of deeper discussion. It's a reasonable assumption to say that m is equal to 0. So in comes assumption number 1 there. A very modest assumption is just a geometric approximation here. The length L, I don't even really need to spend much time on this, is approximately equal to R, doesn't really matter. And here now is a key assumption. What we've done is we've said that the contact length and the contact angle are related to the penetration depth of the wheel. And to describe where this comes from, I would need more time. And frankly, it's not of great interest, and you can just take this as being quite reasonable. And so what happens is the penetration depth increases, the penetration depth of the wheel, your contact length and contact angle are increasing, and I can parameterize all of these curves in terms of the penetration depth. Now that was a mouthful, very quick description of everything that goes into this model, and here is the final outcome, which I'm arguing was very simply obtained. What is being plotted is the horizontal force. This is the resistance on the wheel, lateral resistance on the wheel. This would be drawbar pull in some of the mobility literature, or braking force. This is how much your axle is getting pushed backwards or forwards as a function of the weight, how much weight you have sitting on this wheel for different values of torque. So I'll draw your eye to the first solution here, which is the one in my thesis long ago. We always assumed a towed wheel. And this is going to be really consistent with what was done in my thesis. What happens if you have a towed wheel, no torque? It's just a wheel like the Mindot test roller that you're pulling along the embankment. as I increase the force, the resistance on the axle, the pull force is increasing. The resistance, the drag force is increasing. Now, if I apply a torque, if I'm spinning the wheel in the direction of motion or applying a torque in the direction of motion, a positive torque, what happens is this goes negative. It means that I'm driving the wheel forward. I'm generating thrust. But if I get to a certain value of weight here, I can't keep generating thrust anymore. And in fact, even a driven wheel is going to slow me down. Now I've got a resistance, even though I'm applying a driving torque to the wheel. And then finally, the third case to imagine here, which is shown, is the braked case. If I'm applying a torque that's opposing the motion, of course, I'm going to get resistance immediately, and that's only going to grow as I add more and more weight to the wheel. So I hope you're with me in how we got to here. This is a deeply satisfying, very easily obtained analytical solution. And now the question is it any good? Is it right? So to answer that question, I went, Sam Stanier and I went first and foremost to the solution that I was aware of that is really underappreciated, and a commentary on, how science proceeds. Ian Collins in 1972 did a really careful, thorough, rigorous analysis of this problem, where he actually constructed slip line solutions, used method of characteristics in plasticity, or slip lines, constructed carefully these slip line solutions for different combinations of wheel loading. And everything here is very similar to what I showed, is parameterized by alpha, this internal angle defining the contact length. Now, one of the things, and I guess lessons that I've learned as an academic and lessons for the younger folks out there, is that I think one of the reasons that this paper didn't get much traction in a way, or isn't more appreciated than it is because it's so dense, wonderfully dense in my opinion, but it's very unassuming, it's dense, it's rigorous, and it takes a little bit of time to unfold these solutions that are proposed. So this is what is actually reproduced from the paper. And step number one is really just to take these strange looking curves and plot them in a way that's more compatible with what I just showed before. So on the left is what you've already seen. This is the one that you get from the model that I showed. On the right are these curves obtained through the slip line solutions of Collins. And notice, I guess, first and foremost, how strange they are. It's rigorous, as I said, rigorous, unassuming, dense, and there's a lot that goes into this. It's really quite beautiful, but the solutions are very strange. So again, if you look at the towed case, a wheel that's getting just pulled across the surface with no torque, you can see already I have a multiplicity of solutions here. At a certain weight, I can actually construct two different solutions. If I have the driven wheel, it gets even worse. If I pick a certain value of weight here, right in this line, I can have up to 4 different solutions for a particular value of applied weight to the wheel. So, one of the reasons this maybe didn't get more traction is because it was so strange. And now I'll draw your attention to the fact that these two plots are very similar. The scale, look at the axes here, 2.5, 2.5, 4, 4. Quantitatively, it's a really good match between this very approximate simplified model and this more rigorous analysis that was completed by Collins, which strictly speaking is the more thorough version, detailed version of what I've showed here today. That was a very satisfying result. I've already made this point that I'm an engineer. I will always be an engineer, and I'm not really happy until I actually have some data to compare this thing against. And one of the interesting situations here is that there really isn't that great a data. You'd think it's clay, saturated clay. Haven't we run tests on this before? And the best that I could find, and I have yet to encounter somebody who has told me there's a database of results that I'm missing here. The best I can find is this thesis by Freitag, which is at the US Waterways Experimental Station at Vicksburg. I think it's still what it's called, and I hope I got the name right. They built this big test rig. And in this case, what they did is, which was a mistake in my opinion, I understand what was driving this, is they considered flexible wheels. They considered wheels, tires like the ones that you would actually have on vehicles. This, as you'll see momentarily, introduces this confounding factor that now you've got a three-dimensional, these are really three-dimensional wheels. They're flexible. They're kind of a strange geometry. So the data is valuable, but unfortunately it's not compatible with something that we would want to do comparisons with. What really makes this data wonderful, and it's surprising that this isn't true more broadly, is that they actually did triaxial compression tests on soil. On the soil, they characterized it very thoroughly. So you can see what is reported here as values of cohesion, in keeping with the way that we still educate civil engineering students in the US. It should be called undrained shear strength. If you believe the British school of thought, and I think that's more and more coming to the US, that is the right way to view this problem, they report undrained shear strength values, unfortunately in units of PSI, but we can easily convert and we can get some data. So without going more in detail there, I just want to jump to the end, which is they didn't do a braked wheel, but in this study, Freitag did the driven wheel case. So here's two sets of curves: the torqued, the zero torque wheel, the towed wheel, and the driven wheel. And what I've done here is shift this curve down so that zero is in the same place. And you can see that qualitatively, the curve for the zero torque condition, the towed condition, is very similar to the one that we have from this analytical model. Likewise, what happens when you start to drive is what we're seeing here is you just offset that curve and again get something very similar to what our analytical model is predicting here. And the last note here is that notice that now this is no longer a quantitative comparison. The scale is different: 4, 8, 2.5, and 4. And of course, this is a three-dimensional, as I mentioned, this is a three-dimensional wheel. It's a flexible wheel. If you could do the plane strain case for a rigid wheel, I would love to see that. And then finally, we could actually get a direct comparison, meaningful comparison that says how well this model works. The subject, alas, of future work. We are unable to find data like that. And at the moment, we're not able to generate data like that in our lab, but you'll see what kind of data we can generate in our lab. So I'm going to switch to part 2 of my presentation. If anybody has a question on any of this that you saw, I would welcome it now, or we can save them to the end. Emmanuel, do you have a preference on this? I'm taking a little break, sure, to make sure that people are still there and I'm not just talking to myself in my office.
Yeah, I'd say keep going, Jim.
Okay.
I don't know manual is, so I'll answer.
That's all right, thank you. So here I'm going to switch gears, part 2. And the question that I'm going to start to interrogate now is this method of characteristics approach is very powerful, very limited in the sense that it's a limited subset of problems that we can solve in this way. So how can you do this more generally? And part 2 of my talk now is going to go into how can I construct these solutions. I'm going to have to go to a numerical approach, but you'll see by the end I can use a pretty simple numerical approach. And again, this is autobiographical. This is part of my training at University of Minnesota. The way that Andrew Drescher and I were thinking about limit analysis mostly, and one maybe should still think about analysis mostly, is kinematic methods are a way to get semi-analytical or semi-analytical solutions. So what I can do for a general problem where I'm interested in the limit load is I can break the collapse mechanism. I can consider the velocity field, the flow field corresponding to collapse, in a simplified way. And here we think about it as rigid blocks, triangular rigid blocks that can slide relative to one another. This is a very easy way to construct these solutions, a relatively easy way. The trick to constructing these solutions is you have to make sure for your material that you're obeying the plastic flow rule, you're obeying the jump condition on each of these discontinuities. And if you're doing this semi-analytically, what you do is construct a hodograph that relates all of the velocities V1, V2, V3 of these different blocks in such a way that you're ensured that the jump condition is satisfied. And this lends itself to optimization. It's semi-analytical. I have to use a numerical scheme to find the angles. I can now optimize the angles here. And what you're essentially doing is finding the optimal locations of these velocity discontinuities, these jumps that can appear at different locations. Now, one of the things that I picked up while I was in Australia with the late Professor Scott Sloan is how you can do this in a very different way using finite element limit analysis, which Professor Drescher was never entirely sure about, and we've never resumed that conversation about. I'm now convinced that this is completely legitimate. The way these methods work is that you now use a finite element interpolation to discretize a velocity field, and your objective then is to find the nodal values of velocity that somehow satisfy the constraints, these jump constraints, and other constraints arising from the flow rule. And in this case, because you're dropping in a mesh, you can still think about these edges as jumps. It's right to do that, jumps between velocities and different elements. The thing is that these are now at fixed locations. The velocity discontinuities are fixed in space. They don't move. The question here is, how can we make these two things compatible? There's a lot of power in this. These methods are okay. They're very quick, but sometimes they don't lead to very good solutions, and they're just not compatible. And you can't get the simple solution that you can get with these ones. So what we did was we figured out how to make them compatible, and that is, I'm going to show you a numerical scheme which essentially optimizes the location of these velocity discontinuities when you use a finite element interpolation. And this will make a lot more sense when I show the examples. What I first want to do is go through quickly how this works. So I mentioned these jump conditions that along each velocity discontinuity. I'll go back to the previous slide just to make this very clear. I'll pick this jump, for example. My condition, or probably better still to say, pick this jump, which is between two adjacent regions. This block has a velocity, this block has a velocity. And along this jump, I have to have this condition, which says that the jump is compatible with the plastic flow rule. Here's one way to write it that's going to be amenable to numerical analysis. What's in here are xk, are the coordinates of the endpoints of the jump. These p matrices are just the matrices of zeros and ones. And as I say, this is just going to lend itself to easy mathematical manipulation in a minute. And here is the jump in the normal expressed in terms of coordinates of the velocity jump and velocities between the two blocks. Here is the jump in the tangential component of velocity, and this is the jump condition. The first thing that I'm going to do here right away is I'm going to say, I don't like this absolute value, so I'm going to replace this quantity here with a mu that I don't know yet. And here then pops out, for all of my k discontinuities, I have to satisfy these jump conditions, and I have k equations that, notice, are linear in the velocity and with respect to mu. I can do the usual thing and derive an expression for the limit load in terms of mu and velocity, and I'm going to get a linear objective function, linear in the unknowns. And here comes the trick. This unknown mu that is at the moment just replacing this jump in the shear component of velocity, all I'm going to do is insist that whatever that is, it's greater than or equal to the square root of lambda squared, where lambda now is the original quantity that appeared in the absolute value. And this is a trick which essentially enforces the absolute value and means that I can now use second order cone programming. This is in the canonical form of a second order cone programming problem. If it weren't for these so-called conic constraints here, this might be recognizable, and that's what I'm setting up here, as a linear programming problem. And linear programming problems are, of course, very, very quick to solve, straightforward to solve using modern optimization techniques. That's sort of a standard formulation. Now, the big trick actually in this work, that was kind of known already with what I showed before, if you want to now optimize the locations of the velocity discontinuities, what happens is that the v's in these equations that I just shown become unknowns as well. What do you do about that? Do I have to go to a general nonlinear optimization tool to get this to work? The answer is no. And the solution strategy that we proposed was just linearize about known points. So you have an existing solution that you trust. Linearize about the coordinates for the velocity discontinuities, the velocities themselves, linearize this expression, and then you return to having a linear or a second order cone programming problem. I can also linearize other things that are in here, the area that I need. And one thing to note in this linearization is that if my coordinates, if I keep the coordinates fixed, and I'm sorry, I probably said this wrong. So what happens at the top here are that the x's are now unknown. That's what makes this nonlinear. But if you treat the x's as being known, now you return to the original jump condition that you were using, and you're solving exactly the same problem that I showed previously. So enough of showing formulas and going into the details. Let's see some examples. Here is a slope stability problem, which I think is the most visually compelling example that we came up with. And what you're seeing here is, this is a slope discretized using Delaunay triangulation, just going into MATLAB and meshing this whole region. And the slope here has a height h, certain angle 45 degrees here, and under the action of gravity, this is a classical problem in geotechnics, you're going to have a landslide, a slip, the material is going to move downhill when it fails. Now, if I drop in just a random mesh here, the material is forced to fail along these discontinuities. And you can see that the first solution that I compute here, using the standard formulation that I showed at first, no perturbations here, is very bad, right? I mean, if the velocity discontinuities are forced to be at the locations of these element edges, you get a very jagged looking slip surface, and it's terrible. But now what we can do is start to perturb the solution. That was the second slide I showed. Perturb and solve each time for the optimal locations of new nodal positions and new velocities. Keep perturbing the solution, and you wind up with this, which now looks lovely. This looks more like one of the solutions that we would assume, and looks much more believable. And here's the really nice result looking at the stability number here, gamma h over c. And as I put it this way, as I argued before, probably should be undrained shear strength that I'm plotting here. And you can see, as for this particular solution, as I start to perturb the solution more and more, I very quickly improve the solution. And actually, I don't need to do too many perturbations before I'm about as close as I can possibly get to the true solution, which is known in this case because we can do other analysis techniques for such a simple problem. I'm going to show one more example, which is closer to part 3 of my talk. So this is a segue into the next step. And it's also here to show that I can even start with a really bad solution. This is now a wall, I would say a retaining wall, or in a moment we're going to talk about cutting. I'm pushing on the wall, and the soil is failing behind it. And my first guess here is a terrible one. I've just dropped in some triangles here. I've run the first stage of this optimizer to compute element velocities, and I'm able miraculously to get a solution. I get a solution. The true solution is going to be the Coulomb slip surface here, which is inclined at pi over 2 minus phi, the friction angle of the soil, over 2. And if I perturb the solution, if I'm happy to wait and I keep perturbing that very bad guess, you can see that I'm able to get closer and closer and eventually recover the exact solution here, basically within 55 perturbation steps. So that's the end of part 2 of my talk, which is focused on these solutions that we need for these evolutionary plasticity problems that are somehow fundamental. And I could, in principle, use that to go back to my wheel analysis and see what sorts of new and interesting things I can do there. But I'm going to move to part 3, and I'm going to stick with this idea of passive earth pressure for a minute. Again, hopefully people are still there, still with me. If you have any questions, don't hesitate to interrupt me.
Doing.
Great, and we're still live. So part 3 is now what happens if I keep moving this wall? Remember, I'm interested in soil-machine interaction in a very general way now, certainly for my research trajectory. And what I want to shift to is cutting problems, earth-moving problems. And so I can stick with that example that I just showed, but ask the question, what happens if I keep pushing that wall? What happens if I don't stop? And what is going to happen qualitatively is I'm going to see that the geometry is changing. It's now a moving boundary value problem. I'm going to have a force displacement history. Things are going to depend on the displacement. And I've got all kinds of questions that I can start to ask. Do I have a steady state eventually? Can I reach some sort of pseudo steady state? And the way that I started to approach this problem when I was thinking about this in Australia was, I wonder if this cutting problem, if this translating wall problem is in itself amenable to simplified analysis. And you do as one does if you're engaged with these things. You're sitting at home, you're in Australia, so Stockton beach sand is right there. The beach sand is just down the road from you. You fill up a tub of this and grab a copy of, in this case, it's the Intellectual Devotional given to me by my father, which turned out not to be only an interesting read, but also an interesting research tool. And I was sitting there with this tub of sand, pushing the book along the surface, just looking at what is happening in this region of soil as you're pushing this book ahead. And it turns out that was the genesis of a very simple solution, which I'll show in a minute. But actually what I want to do before showing the simplified solution is motivate this problem a little bit more. As I was thinking about this intellectually interesting moving boundary value problem, I was also thinking, this is everywhere, isn't it? I mean, earth moving problems are like this, agricultural problems. This is Journal of Terra Mechanics work, a famous set of solutions by Godwin O'Doherty. If they're talking about tines, so this is mainly in the context of agriculture, offshore pipeline plowing or pipeline plowing in general. Actually, on a huge scale, in geology, they use this plowing type test as a surrogate for studying crustal folding and faulting. And then at very small scales, you have plowing processes as well. And since then, it's just gone from, oh yeah, I mean, truly this is everywhere. So I've lumped now together, thinking about Australia. This is on in Western Australia here, the gold mines. We do construction, we move earth on a massive scale. We move it for construction and mining, we move it for agriculture. We're eventually going to be moving it. There's NASA challenges now, about how are we going to build out on the moon and on Mars. And creatures like ants, earthworms, rodents, they've been moving earth for a long, long time. So there's no limit to how you can think about these interesting earth moving problems. And I know I'm getting sort of short on time. I think I can present all of what's here. I want to return to this idea of fidelity. So this is work that was done in 2018, and I was doing this I was playing around with this book, in my living room with my patient wife, and not the children hadn't yet arrived, so it was just Rachel that was being very patient with me as I was playing around with this. And later, these chaps who I met at a workshop not that long ago, they showed a really beautiful analysis where they went to great lengths to do the numerical simulation of this cutting problem. There's a huge number of particles here. That's really one of the things that makes this study remarkable. And I won't go into details of it, but notice that in this DEM, discrete element method simulation here, they do this cutting problem, and you can see these bands forming and disappearing. And you can see that there are oscillations in the force displacement history as these shear bands form in the material and then are deactivated and disappear. So keep in mind, this is 2018. The work that I'm going to show was, we published this in 2014. We said, I looked at this problem and said, here is another problem that's amenable to simplified analysis. If I've got a wall, my wall is moving in a different direction now. What I can do is postulate that I have a band, but I have a band at unknown location. Beta now is going to be the inclination of my shear band, and I'm interested in predicting the progression of the shear band, or more generally, at the time, what I was very interested in is predicting the progression of the force. How much does the force P increase as you displace the blade into the material? So you will make the same assumptions. It's sand now. It's not clay. It's plane strain, quasi-static, and here it's sand with just a friction angle, internal friction angle. And I'm going to assume the wall is rough. The force on the wall is P. The height of this material that's being pushed around is H. The penetration depth is delta, like it was even for the wheel. And beta is, I'm going to assume now that it's a single slip surface inclined at this unknown inclination angle beta. From the yield condition and from equilibrium, you can immediately derive, without loss of generality, beyond assuming, I also forgot to mention, I'm assuming this is a straight line. That isn't a strong assumption, that could be weakened. So within the context of these assumptions, or the constraints of these assumptions, I can derive that the force, the pushing force, normalized by the unit weight and penetration depth squared, is given by this function, where I don't yet know the H, normalized by delta, and I don't yet know the inclination angle beta. Now, if you do what is historically done, you now say, I'm going to optimize the force, and I'm going to compute the angle beta that gives me the least force using so-called principle of minimum effort. But yeah, I feel like I'm done at this stage. All I got to do, and you're maybe following along with this too, is now I need to compute this H over delta, and I'm going to use mass balance for that, right? I've solved this issue of what is the inclination of the band using optimization. Now I just need H, and of course H is going to grow as I push the blade more and more into the soil, so that has to come from mass balance, and we can do that. We'll assume that everything that I displace as I'm pushing through a displacement delta winds up in the accumulated material here, and I can just, I'll neglect the fact that there's contraction and dilatancy, and I can then use just the simple volume balance to say that the height has to be equal to this expression here. I feel like I'm done until I actually plot the solution, which you'll see in a minute. And this solution is strange because at some point this inclination of the material ahead of the blade is going to be, it's going to be unlimited. It's just growing unlimitedly, and it's sand, so it's going to start collapsing. At some value of alpha, I'm going to have collapse occurring, and then my solution is just ridiculous. It doesn't make any physical sense. So then you could say, let's fix that problem. If I know that collapsing is going to happen, and actually there's an example of that done in the literature, why don't we just assume from the outset that this angle alpha, the inclination of the moving front of this accumulation of material, is equal to the friction angle. And that's like it's continuously collapsing. It's just sitting at the angle of repose. What that means is that I can derive a new beta in the context of this solution. All right, so I've got two solutions now to this problem. Which one is right? And it turns out neither of them. Because if you plot now the force on the wall normalized as a function of displacement, the first solution that we came up with seems pretty reasonable. That's these solid lines here. If I pick a value of wall friction and stick with it, the force is just growing as a function of how far I've pushed the blade. If I plot the second family of solutions, the avalanching solutions, I get something really weird, that I can't even construct solutions at small values of displacements. The solution blows up. But what's even weirder about these is the fact that at some point the avalanching solution is actually less than the optimum, the one that I attained through optimization. How can that be? Because I was trying to minimize the value of force, and I wound up through my avalanching solution with a force that's ultimately less than what I got through my other construction. So something happened here. I could do this kind of combined approach where I take the least of the two, but what happened? Where was the fallacy in this? And the fallacy was that I didn't optimize everything together. It turns out that H depends on beta, and I need to plug in and I need to optimize that whole expression together. So sort of a surprise in this, which, you know, if you go into the literature, the existing literature on this is really overlooked. And I don't have time to go into the full depths of kind of why this is important, but you can at least appreciate there's two family of solutions and neither of them are right. And in fact, the complete solution comes from putting it all together. You can do it. I'm not going to go into details on that. And the complete solution, in fact, generates a force, a lateral force that's less than either of the other two solutions that I showed. Okay. Now, let's talk about how we can make this a little bit more general still. And I know I'm running out of time, so this will have to be pretty quick. What about these jumping bands? What about these jumping bands? And we saw that the geometry of the surface was pretty irregular. So one thing that we're going to do right away is discretize the surface using nodes and treating, constructing the surface as the line segments between these nodes. And now the solution proceeds as follows: is I can have any band at any location. Beta, the angle of the band can be whatever it wants to be. I'm going to optimize this ultimately, and what the bands that are going to span from the toe of the blade to a node. That's the only thing I'm going to insist on in this solution, so that I can bookkeep things and construct this. I'm going to construct this solution by saying within every increment of deformation, I'm going to find the P star that's the least. I'm going to use principle of minimum effort again. Once I've found a solution within an increment of deformation, my kinematics are really simple. All I've got to do is, I've got a rigid block of material here. I just have to shift the nodes that are moving by an amount that corresponds to my increment of deformation. I've plotted velocity here. I can see somebody's drawing on the screen, which I like. I love, you know, interactive presentations. We should probably clear that. Somebody who's, oh yeah, and oops, resume share. Somebody who's in control of the presentation will have to clear annotations if you want. So updating the kinematics within an increment of deformation is going to be pretty simple. The trick to getting these jumping shear bands, it turns out, is because I'm in dense sand, I have to somehow have softening. And the proposal that's here in this solution is, what I'm going to do is ascribe a state variable to each one of the nodes that's able to track how much softening occurs as the band is sitting on that particular node. And what happens as the solution progresses is that as the shear increases on that node, if the band is sitting on that node, as the shear is increasing, we're going to decrease the friction angle. It's going to soften up to some mobilization length UR, and then it's going to hit the residual value corresponding to critical state for the sand. And that's all I need. I need to introduce softening in this way, and I need to think about a few more algorithmic details. For example, this idea that the material is collapsing. You have to do something about that. Turns out that's fairly straightforward. The overall algorithm, I'm not going to go into all of the details, is just keep going, keep updating your displacement increment, marching forward while looping over. It's a very simple optimization procedure here. You just look at all of the nodes, evaluate what the force should be if the slip surface is on that node, and then, you know, there's a little bit of meshing, kind of thinking about how nodes are colliding with each other that we have to do, and just repeat that procedure. Update find the optimal mechanism, update the kinematics, and just keep marching forward. It's a very, very simple MATLAB script. It's very quick to run. And Now here at the end, let me show what you get when you use this very simple model. If I start it as an example without softening, the peak friction angle is equal to the residual friction angle. Friction angle is constant, is equal to phi. Here's what the solution looks like. I can plot the deformed shape. These lines, horizontal lines are here just to show you what the deformation looks like. Here's the nodes. The magenta line here is just showing you where is the node, on what node are we sitting at as we're marching forward. And below here, I'm plotting the horizontal force if the band was at one of these nodes. So you can see this is optimum. It's always picking the optimum where the force is the least. And the last one here is showing you how alpha, the local slope angle, is changing. If I don't have any softening and I propagate this solution forward, I let it run, what happens is that the band just moves through the soil like a shock. And I get something that looks very much like my analytical solution. I just have this wedge, this wedge of soil starting to look kind of like a triangle that's moving ahead of the blade. No jumping shear bands. Now what happens when I put in softening? A little bit of softening. The peak friction angle is greater than the residual friction angle. Now what happens is the initial solution looks very much the same, but I remain on a band only so long, and then it's advantageous for a new band to form in virgin material. It becomes harder and harder to stay on the old band, and the solution jumps then to a new band, and you start to soften on that band until again it becomes harder and harder to shear on that band, and you jump to another band. And the final solution here is a simple sort of step kind of solution where you can see these deactivated shear bands in the current bands. You can see little dips in the force here that plotted as a function of which node I'm sitting at. And that's the little dips are because I've softened in the region of the band. A last point here, which is kind of interesting, is now it's really critical to think about avalanching because the local slope angle is definitely approaching the angle of repose of the material. And I need to have something in my solution to deal with that. Now I'm at the end here, and I'll breeze through the rest of this and show some recent work by Jaffe quickly. But more I wanted to say, we did the careful experiments. We did digital image correlation. We can see these jumping shear bands. We can measure the horizontal force and the displacement, and the solution works surprisingly well. This simple sequential kinematic approach with softening works very, very well to solve the problem. And this is just, I'm kind of done with my presentation if you like, but I'm going to show you, a couple of quick enhancements that we're working on. Is of course you can think, was part 2 of my talk, was all about how, we're not constrained by these really simple mechanisms. We can have more complicated mechanisms, and using this perturbation approach, it's pretty reasonable to compute these and work with these very simple solutions that are more advanced. You can easily move to 3D, and you can easily think about more advanced constitutive modeling, which is what I'm going to end on. So my former postdoc, Jinhao Chi, a great chap, he worked with me on getting this to work in 3D. We've got that going. I won't go into details on that. Jifei Jin, who's maybe even beaming in here now, she asked the question, what if I put a bit of hardening in my model? Not just softening, but hardening. And I don't have time to go into this, as it turns out, but you get a really surprising result. If you put in hardening, and now these are kind of compaction bands, what happens is that now as you shear on a band, you harden on that band, it becomes favorable to just move away immediately. So what you can see here is that the band inclination angle is just oscillating wildly in the beginning of this solution. It's sweeping through this region of material. And when you're done, finally it stabilizes and localizes strongly, and it stays on a band. But you can see that the final pattern of deformation is, you would never even know that there were shear bands in here. They're just jumping around, oscillating wildly, and it gives a pattern that appears to be diffuse deformation. And we asked the question, Jaffe and I asked the question, do these wandering bands really exist? And I don't have time to go into this, but I can at least touch on the fact that we built, with Jaffe's great help, we built this facility with using a 6-axis robot for actuation, a fluidized bed to be able to prepare loose sand samples very quickly. Here's a little video, and I forgot to optimize for sharing videos. I realized that at some point during my talk. So hopefully this is coming through reasonably well on your end. But in the lab, we can actuate these things quite for different processes very easily. And I'm going to jump to the conclusion of Jaffe's work. She's going to defend here very, very shortly. But she actually did digital image correlation on a loose sample, and she was able to do the analysis to see these wildly oscillating compaction bands. This is a very recent result that we're really excited about that's in Jaffe's thesis. Watch for more on that soon. And here, the video doesn't really show it, but you can see this is plotting volumetric strain, and you can see these transient bands that are moving through the material, which this very simple model is perfectly capable of predicting. Very nice result. So this is going onward and upward, as I say, the soil-machine interaction problem. It's a big thrust in our group. And a talk for another day that, again, Jaffe has been championing is there's even simpler ways that you can start to think about these problems using the idea of VHM envelopes. And I just don't have a time to go into this, but basically you can have an evolving envelope, hardening, softening envelope, where you're just operating directly on the displacements and the forces, and you can get really good results. So this is from Jaffe's thesis. She's able to predict the response of different objects moving through soils at different trajectories really well using this simplified model. And that's it. I'm probably over time. Emmanuel gave me great sort of leeway in saying, you know, we have time, and thank you for that, Emmanuel, and thanks for your patience listening to all of this. I hope there were things in it for you. My big takeaway from this is that these analytical and semi-analytical models, I think, are the high fidelity models. Because I showed you a few examples today where, how would you know of the existence of these features unless you set up the analytical model to begin with? And in fact, it's the DEM, MPM, this should be MPM, material point method, large deformation FE, the more advanced numerical simulations that should be informing us how we should be, you know, seeing the physics of these problems and building these equations. And there's all kinds of ways that you can make this more so. So with that, I'm going to stop sharing my screen, and thank you very much, especially for your patience here as I of course got too excited about things and maybe talked too long. And thank you for your attention. Thank you, Emmanuel.
Thank you, Jim. It's a fascinating lecture. It's nice to see that those old methods are being evolved and applied to those new class of problems with moving boundaries. I think that let's open the floor to, so to speak, to questions.
I have a question.
Otto, yes, go ahead.
You showed, sorry, yeah, thank you. I'm talking about the wheel with the solution the new solution that was published with stress characteristics. And I'm wondering whether that solution is both kinematically admissible and statically. That's question one. And question two is, I don't understand why there would be a lack of uniqueness. Is there, I mean, in my experience, that only happens in those equations if there's a discontinuity somewhere appearing. Is that what's happening?
Yeah, both, of course, very good questions. And let me go back. On your first question, one of the prices that we pay with this simplification, why am I doing this? I can be smarter about how I go through my presentation. One of the prices that we pay by going to this simplification, let's see, I have to move things around on my screen, I'm sorry. Hopefully this works again. Using this simplification is that I've lost touch with kinematics completely. So you're asking the right question. Is it kinematically admissible? Probably not. Probably not. And that's part of my saying that this is a very kind of brutal approximate approach where you're just sweeping that under the rug. And actually, I would expand on your question, which is a question for me too. What happens if you bring kinematics into this? And we have ways we think we can do it in a simplified way, that you could think about the kinematics too and come up with the compatible, kinematics with all of this. But it's tricky, and it's cheating. I'm deliberately cheating by only considering the static solution. That's the answer to your first question. We don't know if it's kinematically admissible, and it kind of, because we've made these approximations, we've lost the rigor of even really knowing what that means anymore, kinematic admissibility. To your second question, which I won't look at Collins' original paper, but I'll look at the replotted one. You know, this question of uniqueness. It's not because of it's because of the geometry. It's not because of anything about the slipline solution itself that you have this uniqueness issue. It's because of you can construct multiple geometries that lead to the same solution. So if I go back to this one, really, you know, what should stand out to you is notice how in solution 1, there's been an assumption made about this traveling region of accumulated material here. A solution 2, notice now the wheel is somehow embedded. And in solution 3, again, it's somehow embedded. And it's the geometry, it's the assumptions around the geometry that are creating this uniqueness problem. And in fact, this is a really nice way of highlighting the effect of the moving boundary. You need to deal with the moving boundary somehow in these problems. And because he's trying to jump, we're trying to jump directly to the steady state here. We don't have any clue about how we got here. We can't answer this uniqueness question because we just jumped to a state and we don't know how we got here. But, you know, to your first point, what's so beautiful about these solutions by Collins is that everything here is perfect, kinematically admissible, statically admissible. He doesn't extend all to infinity, but everything is done properly. So those are really insightful questions. Thank you.
I think there's a couple of questions. I mean, Stefano, you want to go ahead?
Sure. Yeah. Thanks, Jim. Nice talk. I was thinking about the problem where you were looking at the backfill, let's say, of a wall. You're pushing the wall against the soil, and you're trying to reconstruct the failure surface somehow with this. We can call it finite element-like approach. And those concerns reminded me a little bit of considerations about, you know, mesh sufficiency, mesh refinement, and potentially even spurious mesh dependence that you might have when you start having failure zones and things like that. So I'm trying to reconcile, you know, what you said with this background. So what you seem to be doing is that, like, so your elements cannot really capture the failure surface because you don't have nearly enough, and they are not well aligned with the geometry of the failure surface that is going to unfold. So is it fair saying that what you're doing, instead of refining by increasing the quantity of the elements, you're just kind of reorganizing their geometry by keeping them few and big? So is that like an advantage that you're claiming? And part 2 of the question, could that be an antidote against potential spurious localization or mesh dependence or phenomena that might appear when you start having, like, you know, shear banding or failure zones, not having this elements that get smaller and smaller?
Yeah, really good questions. The solution that I showed, it's sort of strange in terms of, there is mesh dependency there. I think the answer to for dense material, the formulation that I walked through in detail, you can expect that the solution depends on the node spacing, and there's no doubt about that. We kind of explored that, and you're actually safer showing. What is fascinating about it is there's sort of a range of quantifiable responses depending on what the node spacing is. So it's ill-posed. You have this fundamental problem of mesh dependency. Linking to your second question, what you kind of see is that the spurious nature of shear band development, it just emerges right from the physics that we're talking about. When you have this physical mapping between the two problems, you can understand why bands are jumping around depending on nodal positions and things. You know, in terms of doing it properly, the way to do it properly is to consider the length scale of the band, and Jaffe did that. So I showed you the kind of brute force version where we kind of swept that under the rug, and you're right about that. But the methodical version is to consider the band dimension and think about how it's deforming in adjacent regions. So basically, you have a non-local model then, and you can then show that you can remove the mesh dependency that way.
Jeliank, you want to ask your question?
Yeah. Hi, Jim. Really great talk. Yeah, I have one question and the other question is a follow-up on what you just discussed about mesh dependence. So my first question is about this finite element construction of the solution space. What if my constitutive law, the plasticity, the U surface has vertex? How you can handle that particular situation?
Yeah. Yeah, in the context of your optimizer.
Yes, because
Oh.
at a particular point that
Yeah.
you don't know what is the plastic strain direction.
Well, one of the things that the vertex is tricky business.
Yeah.
Because I didn't really think about this as we were constructing it, but I have a really nice conversation with Yves Leroy, who actually told me in a really lovely conversation, I think you're wrong. And he's right. He's actually right in that our formulation is incomplete. Because the fact that you have if for sand, when you have a vertex corresponding to zero pressure, you actually can have more modes of deformation there.
Right.
And we're not allowing. The practical, I mentioned this engineering dimension to it. The practical upshot is that you don't see those, right? In the problems that I showed, you're never going to approach the vertex, and you're not really worried about it. So practically, it's not important. And the other comment that I would make is that the second order cone programming problem itself actually is really amenable to dealing with that vertex, because the cone itself has this sharp vertex. In the context of convex analysis, this vertex is no problem for those optimizers. So what you find actually is that when you formulate it in the way that I showed, you're actually much more robust in finding admissible solutions than you are using a finite element approach with a really bad stress integration scheme that's not thinking carefully about how you have to handle stress states that are near a vertex. So it's kind of an interesting, we pay a price in terms of, we can't capture it all, but actually that optimization approach based on large scale optimization, it naturally handles the vertex that at least maybe you're thinking about too, the one for Coulomb and pressure dependent type materials.
Yeah, my second question is a follow-up on your discussion about this mesh dependence. Maybe I'm mistaken. In your model, actually, your finite element itself does not dissipate energy. It's an interface dissipate energy, right?
Yeah, we're mixing two things. So Stefano was asking about, I think, but maybe I got Stefano's question wrong, is that he was asking as I understood it, it was in the approximate sequential approaches where you're discretizing the surface. There's definitely a mesh. I'm going to arbitrarily pick the refinement of that mesh, and everything that I said, holds true. What you're talking about, there is no. Yeah, there's a supreme. Let me share the screen again. I guess what you just mentioned. If I go back to, sorry, the problem with multiple screens is they don't always talk to each other well. The problem here is actually, you're right. All of the dissipation is along discontinuities. You're not worried about what's happening internally. Right. And therefore, actually, there's extreme mesh dependency here. That almost, is the point, is that your solution is going to depend crucially on how you've picked this mesh. And in fact, your ability to generate something that's close to the true solution, if it looks simple like this, or if it looks, relatively simple as it was in the case of the Collins solutions that just came before it, you're going to have to make sure that your mesh is aligned with those discontinuities if you're going to have any hope of getting it. I hope that answers the question. They're kind of two different creatures.
I think
that one is a severe mesh dependency.
Right, but this mesh dependence does not come from the lack of length scale, right? Because if let's for example, if I just input a cohesive law on the interface, right, there will be no mesh dependence on because of length scale. It's because of really the mesh orientation whatsoever.
Right.
Yeah, in fact, if I can jump in, since my question was in fact a hybrid between, I guess, what you inferred from what I said and what Jialiang was getting to. So I was saying that in some sense, you perturb these elements, and then you end up having their sides aligned eventually with that failure zone, so that you force the side behavior, the edge behavior, to be the one that is inducing that bringing about failure. So I can see that it's extremely mesh dependent, but I was wondering if there was almost an antidote against the other mesh dependence that might occur, because you really invoke only the contribution of that one side of the element that is involved.
Yeah, you're absolutely right. And it's interesting to think on the possibilities. Now, if you try to use the perturbation approach, now I understand fully. Sorry, Stefano, you're
Yeah, no. I mean, it was not even clear in my mind. It was forming. It's in a sense you're kind of forcing it to be almost like a cohesive thing there along that particular interface which I identified, as opposed to be a failure in the constitutive, so to speak, behavior of the mesh, the bulk.
Yeah, we've already started to think about how this perturbation idea might extend to fracture, might extend to the problems you're talking about. That's a really interesting question, and the only answer I have in a word is maybe. Future work.
There are a couple of more questions on the chat. Dave Patyondi, do you want to ask your question?
Yes, hello. This is Dave Patyondi from Itasca Consulting Group. I really liked your talk. I have a sort of philosophical question. I liked how you talked about high fidelity models, where you were contrasting computational models and analytical models. And here's the question, because you hinted at this at the end. Were you potentially suggesting that you could use sort of so-called verified computational models as almost like numerical laboratories to help you gain insight into the proper mechanisms, and thereby you could build those mechanisms into your analytical models? And if you do that, how do you have faith that the computational models are good enough?
Right. That is a really good question, and I might just share. I didn't get any time to talk about this in any depth whatsoever. Let me go to the end. And yeah, the hint, there was a really strong hint in here that I didn't get a chance to talk about, is that, here are the numerical simulations. And what is hiding in here is this idea of design feedback, that this is exactly what the philosophical question you asked, is how do I build these analytical models unless I know where to start? And I can use experiments, I can use simulations, but I do have to start somewhere, and they all are kind of informing each other. So I think maybe the answer to that question is, I mean, they're all connected, right? I made it in this provocative way, like which one's the high fidelity simulation, but we need it. And you wind up in this trap that you're saying, that how do you trust the numerical solution to give you good data for the analytical solution? And actually, Qinghao, one of my students right now, he's in that trap right now. He's using a finite element code to generate data, and then he's trying to use that data to inform an analytical model. And it's really a back and forth circuitous process. So you're keeping me grounded here. All of this was not to say that like we don't need high-end numerical simulations. And I think you're right. I mean, the right way, the less provocative way to say it is that there's an interplay between the two.
Yeah, exactly. And you have to refer to your intuition, your thinking, the models, the experiments, whatever you can get your hands on, right?
Mm-hmm. Right.
All right, thank you.
Thank you.
I think it goes back to the old paper by Kundal and Starfield on exactly hitting on the issue. I think, Otto, you had a question. Another question, if you want to go ahead.
Yeah, I'd just like to come back to that, what I talked about earlier about the solutions with the wheel, and also the last one with pushing the dam. You said that you are using statically admissible stress fields and not kinematically, but according to the limit theorems, the statically admissible underestimates the force and the other one over, so rather the other way around. So wouldn't you want to do it kinematically so that your forces are larger than what you need to be on the safe side? That's question one. The other question is, that vertical wall pushing through soil, I've tried numerous times to try to rectify a retaining wall. And what I found in practice is that it's not what really is the limiting force is the force of the tracks on the ground, because you have to push it with something. And I used a bulldozer with very aggressive tracks, and all I did was digging myself into the ground because you just don't have enough friction. So is that done anywhere practically, moving a vertical wall against soil? I'd like to know, because
Yeah,
according to
for
what I,
a project at home, yeah. I think you have to use bracing. You have to jack it. Yeah, you wouldn't. That's an interesting problem, and actually, the problem that you just described makes me think maybe in my terramechanics class, this is going to be a project. This is going to be a homework problem, right? Is you have a wheel that's spinning, trying to push a blade that's pushing into the wall, and now you've got to consider the competition of these two. But yeah, I mean, the answer to the second one, I think in construction practice, what they're doing in Chicago, maybe just telling people what you already know, Otto, is you would jack it in place. You need to figure out how to make a reaction and then jack it. But you can do tilt some kind of inclined jacking, I guess, as well, which would be an interesting problem. To the first point,
yeah, that's why dozer blades have a special shape. It's so you have to be able to let the soil flow. If you really insist on moving the whole thing, you need indeed something totally different, because it's, yeah, even very aggressive practice is a tractor bulldozer, but there's no way, not even a millimeter.
Right. And you'd see that actually, the way you'd see that directly in these models is as you increase the depth to something of the scale that you're talking about, the force just becomes enormous there. To your first question, yeah, we want it to be exact. Whether to use upper or lower. And what you made me realize is that I mixed and matched here, didn't I? I mean, in the first part of the talk, I was doing statics. In the second part, I was doing a kinematic solution. I think the way to answer that is that you can't use the limit theorems anymore. I tried for a while to have this kind of use rigorously the lens of limit analysis to interpret what we're doing. But the fact that your boundary is unknown automatically means that the limit theorems don't apply anymore. You just don't know the boundary, and that becomes a far bigger issue than how you actually construct the solution itself. What do you make if it's a steady state problem? What do you assume for your steady state configuration? If it's a transient sequential problem that you're solving, how are you assuming the kinematics and how are you assuming things evolve? That just completely swamps the question of, is the static solution better than the kinematic solution? And really, you just do whatever you have. And I actually think it's a good question to promote the idea that really what one should do is have everything in there. We should have, the beauty of limit analysis is that, and the bounding theorems, is it kind of constrains you to think about both sides of the solution. And you should feel really nervous if you don't have one side, because you're only approaching it from one direction. So yeah, I mean, it behooves you to think about both statics and kinematics. And certainly in what I showed today, we're not doing that. Eventually, that would be the dream, is that we can unify all of that.
Yeah, I mean, that you are dealing with, as you said, evolution problems, and that's a completely different class of problems. I'd like to ask you a question, because I think that I know it has been for some time that you must be tired, but let me ask you a question. I would like to relate that the blade problem to a metal cutting problem. And what it's observed in metal cutting that at normal speed, at normal temperature, the metal is hardening, so you get this. If you can see my pen here, what you call a shear band. It's a shear shock. And you get this beautiful plasticity solution, stationary solution with a ribbon. But when they go to high-speed machining, where the temperature is increasing, then the material becomes softening, and then you get this kind of stack, deck of cards. Mm-hmm. And I want to relate that to what you said, because I mean, what they observe, and they did some detailed analysis of the kinematics, is that the shear shock then start to advect, is turning, becoming it's a shear band, and then it starts again, because then it's energetically not appropriate. Then it starts again as a shear shock, then advect again as a shear band. So this kind of duality of shear shock and shear band give rise to interesting this kind of decking thing. And I think that there's some kind of relationship with what you are seeing, that when you look at softening in those granular material.
Yeah, it's a wonderful analog, and I'll have to look at that. So my response would be, I'm going to write this down and go leaping to the literature, and maybe we can talk more. But yeah, Emmanuel and I see each other on the semi-regular basis as part of a small collaboration with engineering. So I'll add this to the notes for the next discussion, right? About
yeah, we're involved in a burrowing problem, robot to burrow in soil. I think I really want to thank you for it. It was really wonderful. You can see that from all the questions that you have been subjected to. So I've got a lot of interest. Thank you for this very well presented, passionate presentation. So thank you again on behalf of everyone here in Minnesota and everywhere else. I don't know where you are, but bye-bye. Thank you again.
Thank you so much. Bye-bye. Thanks for having me.